So good afternoon. I'm not sure how many of you are still awake. And this is not a reflection of the presentations that the previous presenters gave you, but I'm sure it's a reflection of the lunch you've had. But I'll try to not put you to sleep completely. And I'm here to talk to you this afternoon about what we've done at Quest regarding fast reroute. My co-presenters here are Sohail Ahmed and Richard Southern from Juniper. And let's jump into the agenda here. So what we'll do here is first talk about what fast reroute is, what are we trying to do with this particular technology, and next we'll talk about why Quest chose to implement fast reroute, why not something else, and then cover a few real-world scenarios of what we've seen with this deployment, and share with you some of the operational lessons that we've learned as we've deployed this particular technology over an 18-month period, and we'll wrap up with conclusions. So to get us into understanding what fast reroute is at a high level and tell us how this technology works, Rich.
Hi. My name is Richard Southern. I'm one of the tech support engineers at Juniper Networks. And I'm here to talk today about what fast reroute is. I'm not going to try to convince anybody to use MPLS. That's a decision that each ISP's got to make by themselves. So when you deploy a network, there's several things that you have to consider. Basically, you have to plan for a failure because those are inevitable. From the tech support perspective, which I feel qualified to talk from, we tend to see two different types of failure modes. These fall into the categories of a control plane failure and a data plane failure. Now these can be addressed with different types of technologies. For example, the control plane failures can be addressed with something like graceful restart implemented per protocol. The data plane failures can be addressed with various layer 2 solutions like APS, link bundling, aggregated links, and so forth. If that network is also running an MPLS cloud, you can then take advantage of secondary LSPs and fast reroute. When you're looking at a network and trying to build some resilience into it, recovery speed is pretty important. How fast is that network going to recover from an event? In the case of using an MPLS-based network with secondary LSPs, if you only have a secondary LSP, that's going to place the burden of recovering the network on the ingress router. The ingress router has to wait for a path message to be sent back upstream, indicating that there has been a failure downstream. The ingress router is also going to be running some IGP most likely, and there will be some inherent delay in the change to the next hop for that IGP. That's going to be an implementation detail that's unique to each vendor. If your secondary LSP is running in standby mode, you are at least going to save a CSPF computational run. Now, some of these delays switching to a secondary LSP is going to be in the hundreds of milliseconds to 1 second range, and during that time you are going to be experiencing data loss. Now, for people who've got the web presentation up, I've realized that there's no animations possible with the PowerPoint conversion. So what I've done on the screen here is tried to illustrate the process that happens for these different types of recovery modes. In the case of the secondary LSP, when an error is detected on the link, a message is sent back upstream, as I mentioned, to the ingress router, and the blue line's already there. And the ingress router will reroute the traffic around the problem using the secondary path. Comparing that now to fast reroute, where each node along the path is capable of making an independent decision to reroute the traffic. These decisions are made by the inclusion of additional objects in the setup messages. The detour and fast reroute objects are the ones I'm referring to. And I wanted to point out that fast reroute can be used in conjunction with other protection methods. So it's not exclusive to fast reroute. You can have secondaries, you can have APS, you can have aggregated links. It doesn't matter what the underlying layer 2 or layer 1 protection method is. Again, talking more about the recovery time for fast reroute, when you have a delay in switching to the fast reroute, that's going to be primarily the detection of the failure. Typically, that detection will also have to include an update into the forwarding table. Because this is all going to be label-based, you have to propagate new labels out into the forwarding table in order to use that detour. Generally, this is in the tens to hundreds of milliseconds window for the delay. However, if you're using something like fast reroute, where the labels are preloaded into the forwarding plane, you can cut that number down dramatically. We've tested in the lab and consistently seen 50 millisecond and less numbers. And for those people who are deploying VoIP networks, 50 milliseconds is kind of a key number in order to be able to keep your voice traffic flowing properly. Now, again, the general disclaimer here is vendor-specific implementation details can vary this number. Then packet loss is going to be minimized just to the packets that were knocked out on the link when it went down. So within fast reroute, there's a couple of different mechanisms that are available. And these are all defined via various drafts. There's no RFC at this point. The authors are working towards something where they all agree on it. But for the time being, there's primarily two different widely deployed fast reroute mechanisms. The first of which is something called the detour. This is currently implemented by both Juniper and Avicii networks, and this is a one-to-one method of backing up your protected LSP. This means, in essence, that each protected LSP has its own dedicated detour to use. Detours also happen to use a combination of link and node protection. And again, the animation's not there on the web, but it is up here. So the blue line that is currently on the screen represents the protected LSP. That's the path that was signaled. And because this path included the fast reroute object, router B and all other routers, but for simplicity I've just illustrated router B, has created a detour LSP going through E and F. You can see the labels that are being exchanged if the fonts aren't too small. And when the link failure actually occurs, router B is going to reroute the traffic using the detour that it has. However, it's going to be swapping those labels. So instead of forwarding with the existing labels, it's going to select entirely new labels. The key difference here between this method and the methods I'm about to talk about is this only uses a single label stack. The other mechanism for fast reroute, as opposed to detours, is something called facility backup, which is an N-to-1 or many-to-one kind of backup mechanism. This means that each protected LSP will be sharing a bypass LSP in order to protect the traffic. This means that there will be one or more protected LSPs transiting that protection, that bypass LSP, when a failure actually occurs. Within facility backup, there's two sort of broad categories. There's link protection and node protection. Link protection is sometimes referred to as Nextop, which is implemented by Juniper, Cisco, Avicii, and others. And then there's the other option, node protection, which is Nextop. Link protection is the one that so far a lot of ISPs have demanded. There is an immediate need at this point to protect the critical links on the network. So that's where most of the development time has taken place. I just wanted to mention that with node protection, currently Juniper doesn't do that, Cisco does, and it may turn out later on that this is a good way to do it. However, graceful restarts may alleviate some of the need to have node protection in your network. This is an illustration that shows how link protection works across the network. Again, very similar to the detour mechanism, the blue line represents the protected LSP. The dotted line represents the bypass LSP that's been selected by router B. You can see the labels. It's a single label stack across the primary path. Now, when a link actually goes down, the traffic is rerouted across the bypass. However, in the case of bypass LSPs, what happens is you're pushing an additional label. So router B will push onto the stack an additional label. In this case, I've just used the value of 100,000 as the label. It can be just about anything. It's a vendor-specific implementation detail, again, as to what values are used for bypass LSPs. When router E receives that two-stack packet, it will pop off the outer label and forward it to router C, and router C will receive the inner label of 200. In this case, this was the originally signaled label, and it won't know that there was a failure that had occurred along the LSP, and it will forward it as if nothing had happened. This illustrates another example, just using node protection in this case. It's very simple, very similar to the link protection example I just mentioned. Again, router C fails, B reroutes the traffic through node F, and a two-label stack is created at B. F pops the outer label, B receives the inner label, thinks it came from the upstream router, which is actually offline or non-existent now, and everything proceeds as normal. Now, when you compare secondaries and fast reroutes, it's perhaps not fair to compare them because they're really complementing technologies. But if you chose a network and just chose to use secondary, there's going to be some things to consider. Secondaries, again, it's signaled and handled by the ingress router, so you have to wait for the ingress router to switch the traffic to the alternate path. However, the good thing about secondaries is a secondary is just another LSP, so it can have its own set of constraints applied to it. Generally, secondaries will also try to stay away from the existing path and nodes, so you've got a built-in fate sharing mechanism with secondaries. However, secondaries do incur an additional management and planning cost, and again, like I said, switching is done only at the ingress router, so you do experience a longer delay. Fast reroute, both the detours and the facility backup varieties are both there to protect the links. However, you tend to have somewhat less control over the path constraint, and both a plus and a minus, you don't have to actually configure anything, so the LSPs will choose the bypass LSPs will choose their own path through the network. Take that as you will. It can be a plus because there's no management required. It's a minus because you don't know where they're going to go. So secondary makes all the same bandwidth requirements and requests as the primary LSP. It can make the same class of service requirements and will remain up after the primary LSP has recovered. This is something that differs significantly from a fast reroute LSP. So when the primary path fails, the secondary takes the traffic, and you might have multiple secondaries. When that primary path recovers, the link flapped for whatever reason, the node crashed and came back up, the traffic is going to continue to flow over the secondary until some sort of optimization timer kicks it back over onto a primary. Fast reroute, on the other hand, is generally considered a short-term fix. You only want to route around the problem for as long as it's really happening. And in the meantime, you want to let the ingress router know that a problem has happened, so you want to have the ingress router handle it, either by switching it maybe to a secondary or by perhaps signaling a new primary path. So at this point, I'll turn it over and learn about actual implementation in a production network of fast reroute.
Thank you, Rich. So all it sounded pretty complicated, I think. It isn't simple. So in these next few sort of slides, I'll try to see if I can get the message across to why we chose to do this in the Quest network. So that's a picture of the network, an attempt to prove that we actually do have a network. So this slide talks basically about the recovery requirements that were placed upon us when we designed our OC192 network. We initially had a set of OC48 SONET APS protected circuits, where SONET protection was giving us about a 50 millisecond recovery time, and then we migrated to an OC192 network, which is made up of unprotected wavelengths, and we needed to provide the protection that SONET previously provided, but at a higher layer. And we wanted this higher layer protection to be of the same order of magnitude as SONET was. And about 18 months or so back, we had our folks from our voice portion of the business come to us and ask us if they could use the IP network for transporting the voice traffic. And of course, their requirements are pretty stringent as far as the recovery times and things like that go. at the particular point in time, we were able to meet most of the SLAs, like latency and packet delivery and those kinds of things, but the network recovery, which we primarily relied on IGP, which in our case is ISIS, was in the order of multiple seconds, certainly did not meet the requirement of less than 100 milliseconds. And we also needed to protect at the sub-second level, both against link and node failures. So what were our options when we looked at this about 18 months back, as we wanted to provide the sub-second recovery times? You could obviously go back and tweak your ISIS timers. In fact, there's at the NANOG this year in February, I think Jengis from Packet Design presented his study on the ISI stability on the Quest backbone, and you can go back and look at that. But basically the summary of the presentation was that the network was pretty stable, but the convergence was in the order of multiple seconds. At that point, we'd done the tweaking we could. This was sometime last year to get it down to the order of a few seconds. Now, it is possible to further improve this with certain enhancements to the ISI specification, and that particular presentation covers that. Unfortunately, we don't have any implementations that take into account all those proposed enhancements. The second option we had was, we still do, is to look at the graceful restart mechanisms. This offers protection against control plane failures when a routing engine goes down. But if your link's flat, you still have a problem. And then there are some vendors who are working on something called stateful failover, where the routing engines actually maintain state, and such that if there are any outages, the routing card, it is transparent to external peers, that is, the peers don't drop. Now, I'm not seeing a whole lot of wide-scale deployments in the production environment here, so we'll have to see how that works. And then we had this option of looking at fast reroute, and when we looked at it initially, it was possible for us to obtain sub-second convergence times. However, we were stuck with proprietary implementations initially, and we had to think about the fact that it was a new technology, and we had to go back and train our ops people on this new thing. In the next few slides, I'll talk a little bit about operational considerations. Like Rich said earlier, the way we implement fast route on a network, if a link fails, the traffic is rerouted over the backup, the primary is re-optimized, and all this happens transparently. So in theory, you don't really need to be monitoring anything for fast reroute because you're already monitoring your links on the network. So if a link goes down, you get alarms indicating that a particular link has gone down, and you can react to those links and let fast route do its job as transparently as possible. Now, this can be a good thing or a bad thing, depending on how you look at it. However, if we do have problems with the control plane, now those problems are much harder to detect. It is a new control protocol, so people are still learning this, but fortunately for us, we haven't had a whole lot of problems so far with that particular issue. I mean, we've had little bugs like as a first implementation, but things haven't really, gone south completely. In the worst case, if fast route completely fails to work, the IGP is always available to resolve your route. So the worst case scenario isn't that worse than what we currently have. Here I basically talk about a few things that we had to consider from an operational standpoint. We had to think about monitoring tools. The SNMP functionality that is available today can do with more work. Traffic management, we don't really do a whole lot of traffic engineering, so that isn't a real issue for us. And we had to educate our operations folks in the changes that have occurred to the control plane protocols and also the data plane paths. And we wanted to make sure that we don't really introduce this new protocol and make things worse for ourselves. So we want to make sure that the IGP backup, or the fact that the routing can always fall back to ISIS actually works. And initially, to the extent possible, we wanted to keep all these changes transparent to the NOC. So like I was explained earlier, all these things happen transparently. So the NOC really doesn't have to react to changes in the fast reroute topology. They just need to react to changes in the physical topology. Usually when there's a physical topology change, a link fails, that's when your fast route is triggered. They can go back and fix the link and let fast route do what it was doing. And now I'm going to hand it off to Sohail, who's going to talk about a few real-world scenarios that we've seen on our network that will give you a little better sense of how this is working.
My name is Sohail. I'm the lead engineer from Test Integration Group from Quest. So Richard pretty much covered all the theoretical portion of the first reroute, and I'm going to explain like 4 different examples that I have, and this pretty much real world scenarios and what we experience after deploying the first reroute. My first example is pretty straightforward, a link failure scenario where I have a detour link. Primary link's configuration looks like is between Chicago core 3 to JFK core 1. It's a single hop LSP, and for this primary LSP I have a detour LSP which is going to build along Chicago core 3 to Chicago core 2 to JFK core 2 to JFK core 1. I'm not going to go for every single LSP with all the EROs, but my primary goal is here to just go over this outage scenario. So in my first example is when I have my detour failure, when the detour link fails, the Chicago core 2, which is going to send a path error message to ingress router Chicago core 3, and Chicago core 3 going to run CSPF, going to do a CSPF calculation and going to recalculate a new detour for the primary LSP, and the new detour going to establish along Chicago core 3 to core 1 to EWR core 2 to EWR core 1 to JFK core 2 to JFK core 1. The one thing to notice here that when it's built at detour LSPs, it's avoided both link and node where the primary LSP has been built on. On the second example, when we experience the primary LSP or the primary links, when primary links goes down, and in this case, the traffic would immediately shift to the detour, taking the effect of the milliseconds of convergence time here, but we're going to lose very minimal packet in this case. And then this, after this ingress router again going to have its own CSPF calculation, and is going to build a new primary, and in this case, the new primary will be the existing detour, so build up on the existing detour, and for that new primary is going to build a new detour. And I'm not going to go in details because there will be more detours along the path, but in the picture, you have a pretty good picture over here. So, and the third example that I have here, where I have both primary and detour LSPs are riding on the same fiber path, and if we lose or if there is any fiber cut along the fiber route, we're going to lose both primary and detour LSP, and in this case, the MPLS fast reroute fails, and we have seen that in this particular cases, the routing falls back to traditional IGP, and there's other features that we're looking into it, and fast phase sharing is one of them, and it may have a solution to this type of outage scenario. And my third and my fourth example is very typical, which we have some sort of node unstable in the network, and if the links are constantly flapping, MPLS comes to rescue here because most of the traffics are transiting over the unstable router, already been taking the detour path, and we also you can configure the optimization timer, and it allow operation to have ample time to make sure that they are doing real good troubleshooting, and when the router becomes stable, everything falls back to the regular path. So I have some very common troubleshooting tips. I'm not going to go over that, and pretty much self-explanatory, and I think we all use this troubleshooting tips. So I'm going to hand it over to Shankar again.
Thank you. So, to conclude this presentation, we'll talk about what we learned from these experiences and what I think you might also possibly learn from our lessons, from our experiences. So, sub-second protection for both control and data plane failures are necessary in our network simply because we are carrying voice traffic. Fast Reroute provides a sub-second recovery from data plane failures today. The ISIS convergence can be improved, but to my awareness, the best times that we can do is still in the order of multiple seconds. Fast Reroute works, but it comes at a cost. You have to implement a new technology to train your operations people. It lacks a lot of widely interoperable deployments. So we're still working with our vendors to make interoperability a reality. And it's not perfect. It still needs a lot of enhancements, things like detecting the data plane liveness. When you set up an LSP, you don't really know if you can send packets through it. Things like SRLG, where we want to take into account that some of the LSPs are actually transiting fiber conduits that are shared. And other things like quality of service and traffic engineering, which we really do not widely use in our network. But for those of you who wish to use that, there are things that still need to be worked on. And it certainly can do with more manageability improvements, particularly if you're doing a lot of traffic management. The other HA mechanisms that we talked about, such as graceful restart and stateful failover, are interesting to look at for control plane protection. And the thing that we wanted to do as much as possible is to keep this as simple as we can. We rely purely on IGP metrics to build our LSPs, and therefore we don't really explicitly route traffic in different ways than the IGP would normally have. So we're not doing a whole lot of traffic management. And if you do wish to use traffic engineering, the only scenario where we see using it in our network will be to protect against severe outage scenarios where you have multiple failures and you still have real-time traffic that you must absolutely protect. The IGP convergence timers also need to be improved. That is also something that we're working with our vendors. In our implementation, the fast reroute is deployed only across the core, so we still need the protection to happen at sub-seconds across the edge links. And the reality of the deployment today is we really don't know how scalable the control protocol is. We've done a lot of testing in our lab. We have this deployed in the network, but we don't fully know the limits of how far we can take this. So that is something that is work in progress. And that's all I had for my presentation, and I'm more than happy to take questions. Not even one. All right, thank you.